Um, so, so the great themes of historical geology include deep time, plate tectonics, and the organic evolution. This slide describes about the deep time and the age of the Earth uh, based on the evidence we found in rocks was determined to be about 4.6 billion years. Billion, B-I-L-L-I-O-N, billion years. So no reason. No wonder we call the Earth's time as a deep time. It's a pretty long time, right? 4,600 million years or 4.6 billion years. Um, so Earth processes take a pretty long time. About 4.6 billion years is a is enough time for geologic processes to 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 change Earth materials and record the events in them, right? So deep time. That's the reason why we call the time involved with the Earth processes as deep time. Plate tectonics. Why is plate tectonics one of the major themes of historical geology? Well, there's a good reason for that. Now, for example, let's look at South America, Africa. Look at the match between the east coast of South America and west coast of Africa. They look like two pieces of a puzzle together, but now separated. And guess what happened due to the separation? Atlantic Ocean formed. Same thing with North America, that part of North America and this part of Africa. They both match. So was North America together with Africa? Sure. Geologic evidence suggests that. And what is it to do with anything about Earth's history? Well, it has a lot to do about Earth's history. Now, the reason, because when the plates shift, they make mountains, they make volcanoes, they can shake rocks and make earthquakes, they can make Yellowstone to erupt, they can make animals to go through changes, like migrate. If there is a new route, they migrate from one um, continent to another. And if the route got cut off, migration may stop. And then they change through time into a new set of genera and species. So shifting plates um, made a good record of geologic events in rocks and also affected life forms and might perhaps shifting plates were part of the reason why some groups of organisms went through organic evolutionary changes. So no wonder plate tectonics is one of the major themes of Earth's history. How about organic evolution? Why is one of the major themes of Earth's history? Now, if we go back to that slide with the geologic timescale, which is right here, which is this one is a geologic timescale. You see subdivisions here, and you see numbers right here. These are particular ages, right? And right here, you don't see numbers. You see invertebrates, fishes, land plants, amphibians, reptiles, mammals, birds. What does it mean? It means that these groups of organisms appeared at different times during the Earth's history. And why is that important? Well, it is important because they let us identify the age of rocks, a relative age of rocks. So no wonder the the changes the organisms went through helped us understand Earth's history. because of the changes that occurred to them, they appeared in the rock record at different times. So it's definitely they have a strong significance in terms of Earth's geologic history. So like these Ammonites, for example, they were living, thriving all the way up until the end of Mesozoic, and they went extinct at the end of Mesozoic. So what did happen? Well, if you see a fossil of Ammonite, for example, it could be that its age is about, it can be Mesozoic, but it can never be the younger than Mesozoic. It got to be older than Cenozoic because they did not live during Cenozoic, which is one of the divisions of geologic time. So fossils, which are the connection between organisms like these that we see in this on this slide, which are ammonites, and us, which are who are us living right now, we have never seen this group of organisms in their living form because they're no more living. They went extinct. So such changes that occur to life forms helped us to place the rocks in a time sequence. So that's why the organic evolution is one of the major themes of Earth's history. There it is. Geologic time, plate, tectonics, and organic evolution. These are the major themes of Earth's geologic. So that's why in the next chapter we'll begin to talk about geologic time. That's going to be our next topic, right? Now, before we go to that topic, Joel, do you have any questions? Do you have any questions about geologic, the chapter 1, Introduction to Historical Geology? Okay, I see that you don't have any questions. So let's move to chapter 2. Text is just okay, Joel. But if you want to switch to mic, that's fine too. It's up to you. Yeah. All right. So then let's look at this second chapter. It's about principles of historical geology. What are these principles? These principles help us to place geologic events in a time sequence. And what is a time sequence? Let's take some examples from our everyday life. Now let's see. Let me tell you what I do every day. During the work week, this is a logical sequence, and this applies to anybody, right? I believe. So you get ready, wake up, get ready, eat breakfast if that's what you do, right? Go to school, go to work, do your work, finish your work in the evening, go back, eat your dinner, right, and rest. And this is nothing hard to understand. That's a logical way, right? We do things. We don't eat breakfast and sleep, right? Relax and then work. No, that's not how we do every day, right? So it's a logical sequence that we follow, and we adapted this. And well, imagine you're trying to do the sequencing of events in terms of geologic processes. Now, with us, we can observe a human being going through these changes, these scheduled events, or maybe this human being has a record of some sort, the work schedule, and so on, and so on. There must be some record that one can read, observe, and understand. But the record that we have for Earth's geologic events is written in rocks, not in the language that we know. We have to find a way to read this code. And that's where these principles come in. They sound very simple, but very powerful. Invented a long time ago, right? Still useful. So we'll go through some basic principles of historical geology in this chapter. First one we'll talk about will be about Steno's laws. Look at the lifespan of Steno, 1638 to about 1686. It's 17th century. That long time ago he formulated these laws and still are useful. What are these called? Principle of superposition, principle of original horizontality, principle of original lateral continuity, right? These are the names of these principles. I want you to recognize them as the names of these principles. To the right, you have a figure, and what we see here are sedimentary rocks, right? A, sedimentary rocks deposited in a sedimentary basin. No more, there is a C, it's now rock. And B, well, this area went through some erosion, and that's when this part got eroded, this part got eroded, and even the top part right here, right? We don't see the entire thickness of this top layer, right here. So erosion removes materials. Now, if you think about it, there are two events right here. We can say that these rocks formed, right, deposited in the basin. That's the first event, and turned into rocks, second event, and then got eroded, third event, right? But what if we don't know about this deposition and we are looking at this area without knowing what happened in the past? Can this area lead to all these events that we missed to observe? Sure, that's where the Steno's laws come in. If you look at this principle of superposition, oldest rocks on the bottom, younger rocks on top, meaning the rock right below right here is older rock compared to this rock, right? Principle of original horizontality. Sediments are deposited in flat horizontal layers that we can see here. If they are not horizontal, then it's another event that occurred after they formed. Principle of lateral continuity. And if you look at this here, B, figure B, they are not shown continuing laterally because you see a break here. You see a break here. But Steno says, well, Steno said that sedimentary rocks do not form this way. When they form essentially like this. They don't form like this as bits and pieces, unless there are some exceptional conditions. When they form like this. They extend long distances. For some reason, if they don't, like here, then something has occurred. So that's how we know that these rocks did not form this way. In B, they formed essentially like what is shown in A, and then got eroded. So that's Steno's laws. We can apply it here. You see, if you look at this river here, if you dig into the sediment of this river gravel, well, you can apply those Steno's laws. That near the top, that's the youngest gravel. If you dig deep, that's the older gravel. Or if you look at these rocks right here, this is the oldest rock at the bottom. This is the youngest rock near the top. And if you observe closely, it looks like this rock right here and maybe this rock right here, they look similar. Is it possible that this rock extended from there to there? Sure, that's what Steno's um, original horizontality says. But then what happened to this part of the rock? Well, river came later and eroded it away. So there you go. So these rocks formed first, right? Along with this area was part of it. This area was part of it. Oldest rock formed first, youngest rock formed last, and maybe some other rocks. And then this area got eroded, and the river came in later. So that's the history of this area. You see, Stirner's laws were pretty useful. Some more principles. Cross-cutting relationships. Faults. Perhaps you were introduced to faults in physical geology. See this line here? That's a fault. And you can see along this fault, the rocks have moved. Look at this rock here, the one with the brick pattern. See, it shows up on either side of the fault, but it looks like it broke and moved along the fault line. So fault is younger than the rocks it cuts. So this rock in brick pattern is older compared to this fault. There you go. That's what this principle says. Yes? How about intrusions? Principle of intrusions. Igneous magma has a tendency to intrude the rocks. See, this is intrusion 3. Sedimentary rocks are older than the igneous rock which intrudes them. So layered rocks like this brick pattern rock, these dashes, sedimentary rocks. And you can see this 3 igneous rock has intruded the sedimentary rocks. So according to this principle, sedimentary rocks are older than the igneous rock which intrudes them. So number 3 is younger, and the sedimentary rocks, layered rocks, are older. That's what this principle says. Right? So then this figure here has an intrusion, which is this one. So that is younger compared to the rock on either side of it into which it intruded. So that's what it means. How about the principle of inclusions? What are inclusions? There can be gravel clast intrusions and xenolith intrusions. And I wanted to get this. These here, these are the gravel clasts. These fragments in brown present in this rock layer, yellow in color with dots. That's how the gravel clasts are going to be. Inside the granite, you see fragments of sandstone. Those are xenoliths. So gravel clasts are present in sedimentary rocks. Xenoliths are present in igneous rocks like granite. Pieces of gravel, which are gravel clasts, are older than the rock which contains them. So in this case, the pieces of gravel are older, they formed first, right, compared to this sedimentary rock shown in yellow with dots, which is actually sandstone. How about xenoliths? These are present inside an igneous rock like granite. Xenolith is older than the igneous rock which contains it. So in this case, sandstone xenoliths are older compared to granite. So you see, both of these figures list granite, sandstone, shale limestone. Granite, right? Granite, sandstone, shale limestone. Granite, sandstone, shale, limestone. But because sandstone contains gravel clasts of granite, it is younger compared to granite. meaning granite got to be there already before sandstone came in. Granite formed first, broke down, and then the broken pieces of granite got into sandstone. Sandstone is later to granite. Sandstone is younger than granite. Granite is older than sandstone. So that's A. If you come to B, fragments of sandstone are seen inside granite. The only way it can happen is granitic magma intruded sandstone, meaning sandstone is older compared to granite. Granite is younger, right? Granite came later to sandstone. You can see how these materials are useful in coming up with a time sequence. How about unconformities? What are unconformities? Unconformities are surfaces of erosion, meaning, let's look at these rocks here. If you observe the rocks right around here, they have this kind of inclination. Yes, you can. I think you can see it, right? Come here, this part, they are almost vertical, right? They're vertical rocks right here. How come we have vertical rocks right here and kind of inclined rocks right there? What happened to them? Well, that's this line of separation right here. How can this happen? We just studied the Steno's laws. Sedimentary rocks do not form this way. Sedimentary rocks form in a horizontal manner, not an inclined manner or a vertical manner. So that demands many historical events. So since these are at the top, there is a good chance that these are younger rocks compared to these rocks. There you go. These are older rocks, older set of rocks. These are younger set of rocks. Even older set of rocks. There is some history here. They formed horizontally and they became vertical, tilted. And then they got eroded along the surface. And then these rocks came in, younger rocks, and the entire area got tilted. See, that's the history of this area. It's a real world scenario. So then this becomes unconformity, which is this surface of erosion, like this one here, number 4 in this figure. Right? So the unconformity is younger than the rocks that have been eroded. So in this case, these are older set of rocks because these rocks were eroded to make this unconformity. So these are older rocks and unconformity is younger. So then 4 is younger than there are all these rock layers and other things that got eroded. That includes sedimentary rocks, intrusion, faults, all of them. All of them are older compared to the unconformity. See, all these principles are extremely useful when you're trying to put them in a sequence. Now, to help us understand how the unconformity is formed, we have a set of figures. 1, 2, 3, 4, and 5. So this is the history of this location shown using illustrations, right? So these vertical rocks, this older set of rocks, formed first as horizontal layers, and then they got tilted. Maybe due to some compression, they got folded. Maybe a mountain formed then. And then they got eroded because mountains erode. Water came in. So now we have tilted rocks covered with water. If you have water, there is dust. So the tilted rocks were covered with dust. The dust turned into a sedimentary rock, and the entire area got tilted again. See, that's the history of this area. All right. So we put together all the principles we learned so far to understand how this area uh, went through the geologic changes. Any questions so far, Joel? Are you with me? Do these discussions make sense? Okay, that's good. That's good. Um, let's see. Now, the last principle that we will talk about is fossil succession, principle of fossil succession. And uh, this principle recognizes that fossils occur in a consistent vertical order in sedimentary rocks all over the world. And this figure here gives us a basic understanding of how these changes occurred. Um, the life forms that appeared first were very simple organisms with one cell making their bodies, to all the way to our the current generation, the most complex life forms with many organs, multicellular, multi-organ containing bodies. So how did this change occur? A simple submicroscopic size organisms, single cell organisms, to multicellular organisms, to um, multi-organ, multi-complex life forms, right? And it did not occur in one day. That's what the record suggests. It occurred in a time sequence, and this principle suggests that fossils appear in the rock record in a consistent vertical order, meaning um, when when invertebrates first appeared in the rock record, we had no record of these organisms in those old rocks. Meaning, if you study rocks that belong to Proterozoic or early Paleozoic age, you will never find fossils of fishes or fossils of land plants or fossils of mammals, reptiles, birds, amphibians. Nope, right? They begin to appear later, in early Paleozoic or Proterozoic, Phanerozoic eon, not during Proterozoic eon. Likewise, if you search in the rocks um, of Cambrian, you may not find the fossils of land plants or other set of organisms that appeared later. No dinosaurs in, say, Paleozoic era rocks. They appeared and change and changed, right? Undergone evolutionary changes during Mesozoic. So that's another principle of fossil succession based on the fossil content of rock layers. There is a way to place the geologic events in a time sequence. So then let's put the events that are shown in this figure in a time sequence using all the principles that we studied. Now, luckily, these are numbered in a time sequence. 1, then 2, then 3, 4, and 5. Let's try to explain, let's try to understand what these events are. Now, Joel, can you tell me number 1 event? Is it showing a formation of sedimentary rocks, or igneous rocks, or metamorphic rocks? Can you choose one of them? Well, there are plenty of clues in the figure that you can use. The event 1, what is it showing? Is it showing sedimentary rocks, igneous rocks, or metamorphic rocks? Can you choose one? Well, use these names: shale, sandstone, limestone. What type of rocks are they? Sedimentary, igneous, or metamorphic? What do you think? Well, these are sedimentary rocks, right? Because, oh, yes, they are sedimentary. So let's see. Oh, I didn't know that I can increase the size. What did I do? Oh, like this. I was trying to increase the size, but anyways, oh, there it is. Did you see the change in the size of the screen, Joel? Did the size of the screen increase on your side? Oh, okay, okay, then it is only on side. Okay, that's fine. So then I was trying to increase the size here. Okay, let's see. So, oh, these three are sedimentary rocks, all right? And this one is igneous rock. So the sedimentary rocks require a sedimentary basin, water basin. So they were collected in this water basin, turned into a sedimentary rock, and then this event occurred, faulting. So faulting is breakup of rock and movement of rocks along the break. So when this happened, the sedimentary rocks got deformed, broke, and moved. That's the second event. And then intrusion came in. Why is intrusion after the fault? Because if the intrusion was already there, the fault would have affected it, right? So we would have seen even the igneous rock, in a broken form, like what this brick pattern is showing, right? Along the fault, it broke and moved. Like that, even would have seen igneous rock broke down and moved. But that's not what we see. Igneous rock is fine. It went through the fault. So that's why 3 is after the fault, not before. So sedimentary rock formation, faulting, and then the intrusion. And then the erosion came in. Why do we think erosion is after that? Because I see erosion cut through the fault, cut through the igneous rock, and then the sedimentary rocks. All these events were eroded. So 4 later. And then all these sedimentary rocks came in. See, that's the history of this area, right? So if you go to any such a location, like if you go to say, there are some locations like, I don't know if you have been to some parks in the state of Texas, Pedernales Waterfall Park. I encourage you to go there. It's about 5 hours away, 4 hours away from here, San Antonio, near San Antonio. Very nice park. Very nice park where you see layers of rock, sedimentary rocks, limestones. You will see some of these, concepts useful. So if you have a chance to go to San Antonio next time, don't forget to visit Pedernales State Park, right? And when you go there, take these principles with you, understanding of them, and see if you can use them there. And then this chapter also goes over some conflicts of ideas like Neptunism versus Platonism, catastrophism versus uniformitarianism. We'll briefly go over them, not in a very detailed manner. What is Neptunism? They believed in sea, ocean. What is Platonism? They believed in some Earth's interior processes that happen inside the Earth. So Neptunists believed something that happened at the surface of the Earth in the water, in the sea. Plutonists believed in something that happens inside the Earth. and there was a fight. Neptunius said all rocks came from the sea. Were they right? Partly. Sedimentary rocks, actually, some of them come from water. Limestone comes from water. Gypsum comes from water. Salt comes from water. All these are sedimentary rocks. How about granite? Nope. It comes from magma. Basalt comes from magma. So that's where the problem was. Neptunius and Plotinus, they had a conflict. Those two are conflicting ideas. First, Neptunius explained the formation of rocks as materials that formed from the oceans. Then Plotinus said, hey, look at this volcano. It's bringing lava to the surface. And then we see the formation of a lava rock. How can that be a rock that formed from the water, right? They could prove that rocks, some of them, can form from water. I'm sorry, from material like lava, which comes from inside the earth. So Plotinus had a point. Neptunius are partly right, because some rocks do indeed come from water, that is, water of the sea, but not all of them. So Plotinus said, hey, if water could make all these rocks, where did that water go? Think about the salts. How much water needs to evaporate to make a thin layer of salt? Too much. To make the mountains, like huge mountains like Rockies or Appalachians, Sierra Madres, Himalayas, Alps, it requires huge, extremely large sized ocean. Where did it go if ocean could deposit all the rocks? So that's what the Plotinus point was. And then they could prove that lava comes from the earth, inside the earth, not from water, and makes lava rocks. So that's their fight. I let you read about these ideas in the book. Likewise, catastrophism and uniformitarianism. Catastrophists believed that changes that occurred during the Earth's geologic history were catastrophic in nature, sudden, extreme changes. Uniformitarian believe in a steady rate of changes, not catastrophic, but steady rate of changes. Catastrophists showed the evidence of a sudden change in the fossil record. Uniformitarianists said, no, those changes are not due to abrupt changes, but because of unconformities. That is, unconformity erodes the rocks and takes away the evidence. And you go from older rocks to younger rocks across an unconformity, of course you're going to see sudden changes because some evidence is now missing. That's the reason why you see these sudden changes in the fossil record, but not because of catastrophic changes. So then there was a conflict between catastrophists and uniformitarianists. And now we know that they both are needed to explain. Because some changes were indeed sudden, like meteorite impact or sudden extinction of organisms. But not all of them, right? Some required a steady state of changes. So we think we now had to adapt both these ideas into another new concept called as actualism. So I would like you to read the book and understand more about these ideas. The people who suggested these ideas came up with evidence and the details, right? I also want you to study the geologic history of North America, like who helped us understand helped us in our understanding of geology of North America. Like, for example, why did we think that there was ice age that that occurred in North America. What happened to that ice now? It disappeared. But how do we know that it was there? Well, there was a scientist who understood glaciers because he studied them in Europe. He came to New World and said, "Hey, geez, that looks like an area that was affected by a glacier." Thus came the Ice Age. There was this man who lost his hand in the Civil War, but that didn't stop him in exploring Grand Canyons. He rafted through it, took a lot of risk. So developed our understanding of Grand Canyons. There was another geology interested person who made Yellowstone, right? The first national park of the country. There were a couple of bone collectors. They were interested in dinosaur bones. Fought really hard, but they discovered new species of dinosaurs. So through time, we developed a good understanding of the geology and the geologic history of North America, right? I encourage you to study the details of that, right, in the book. So that's basically it, Joel. That's the chapter on what we call as relative time methods. So the principles that we talked about, they give us an idea about the relative time, meaning we really don't need to worry about the numbers. We just, if our goal is to list them in the time sequence, oldest first, youngest last, and the rest of them in between, then we don't need numbers. Like we said, the rocks of one formed first, the event 2 next, the intrusion occurred next, and then rocks were eroded, and then the 5 rocks. We don't need to know when they occurred, right? So that's a relative time sequence. If that is our goal, principles of geology help us, right? But what if we want to know when exactly these events occurred? How many years ago? That's where the chapter 3 comes in. We call that kind of understanding as absolute times. Relative time dating and absolute time dating. Dating which involves, right, in developing an understanding of time aspect of these events. If it is relative time dating, we are worried about time sequence only. If it is absolute time dating, we need numbers, right? We'll talk about it during our next session, all right? So that's all for today. This is what I wanted to talk about, Joel. Do you have any questions? Oh, you're posting something. Okay, so do you have any questions, Joel? All right, so then same day, Thursday, about the same time. So I may have these meetings every week, but if only few people attend, I may have to think about doing this every week. All right, because if only one person attends, it doesn't make sense, right? So